Good afternoon, everyone. My name is Feng Xiubin, a PhD student from City University of Hong Kong. Today, I will share experience of deploying our system called DEMO, a practical real-time indoor delivery monitoring system. This work is a joint effort with the City University of Hong Kong, the Hong Kong University of Science and Technology, the University of Minnesota, and the University of Southern California. The subway stations in Hong Kong resemble small malls, densely packed with shops and bustling with people, especially during peak hours. Queues to enter stations are common, leading to crowded conditions. These shops offer a wide variety of goods and services, ranging from cafes and convenience stores to home living and banks, lying in a corridor. Delivering of goods to these shops is a daily occurrence. Delivery of goods to these shops is a daily occurrence. Delivery workers navigate through the subway stations with their trolleys, sharing the space with passengers because there are no dedicated delivery pathways. As we know, outdoor delivery accidents often occur, but according to various reports, accidents resulting from non-standard delivery indoors are also very common. Accidents such as goods falling pose a danger to passengers, potentially causing injuries. Therefore, Hong Kong government proposed to regulate the delivery process, especially in crowded subway stations, to ensure passengers' safety. Based on current observation, Hong Kong government has identified 4 types of common violations. Among them, speeding and unauthorized use of passenger lifts are particularly concerned, with goods being prone to falling or colliding with passengers. The other 2 types are delivery goods of designated routes and during peak hours. For example, as indicated in the slide, the red dots represent the delivery route of the trolley, which is not within the authorized areas. Before our system, supervision of deliveries within subway stations mainly rely on hiring safety staff. This staff would accompany workers during deliveries, record delivery details, observe and intervene in any violations. Clearly, relying on human supervision had many shortcomings. First, it's challenging to assess the actual speed of delivery trolleys through observation. Second, with each safety staff only able to accompany 1 trip at a time, other deliveries may be missed. Third, in Hong Kong, labor costs are very high. To address these limitations, the Subway Corporation wants to have an automatic system that could offer reliable monitoring. During deployment of our system demo, we encountered various challenges. First, the Subway Corporation expressed concerns about protecting passenger privacy and rejected the use of camera-based solution. Additionally, they didn't provide cable laying or network cables, requiring us to set up our own infrastructure. Furthermore, they emphasized the importance of minimizing deployment and maintenance costs, and ensuring that the existing layouts of the subway stations remains intact. By the way, we also found that the magnetic field signals within the subway stations are extremely unstable. Unlike other sites, such as shopping malls, the magnetic field readings at fixed locations are relatively stable. Moreover, there were uncertainties regarding how delivery workers would use the sensors provided by our system. To fulfill the requirements of the Subway Corporation, we proposed the DEMO, an indoor delivery monitoring system. DEMO uses Bluetooth Low Energy and Inertial Measurement Unit readings to achieve speed detection, positioning, and monitoring functions. It has been successfully deployed in 12 subway stations in Hong Kong and has been operational to date, covering over 200 shops and overseeing more than 40,000 deliveries. DIMO utilized the SSI2 distance model for indoor positioning. Common fingerprint localization technologies face several limitations in a large-scale deployment. For example, they require a significant amount of manpower to complete data pre-collection and testing, as well as frequent updates to the fingerprint database, which consume a lot of time. In comparison, while the SSI2 distance model may not be as precise as fingerprint technology, it offers simple deployments, easy scalability, and low costs. Moreover, in our experience, due to the similar environments in subway stations, a small amount of data collection can also achieve decent accuracy across all subway stations. Our system consists of two components, offline preparatory and online operation. During the offline phase, we prepare and install our necessary hardware, collect data, and test the accuracy of the SSI2 distance model. Additionally, we also pre-process the floor plans of the sites. During the online phase, delivery workers will pick up the sensors in the entrance, and sensors are mounted on the delivery trolleys for real-time speed monitoring and indoor positioning, enabling the detection of various violations and alarms if necessary. Our system consists of two hardware components, the transmitter BLE beacons and a receiver customized Raspberry Pi. We choose small-sized battery-powered BLE beacons, which can be installed at skirting board locations near the ground. This will not destroy station's aesthetic design. Each beacon costs only around $9 and can operate for up to 2 years. As a receiver, we customize a Raspberry Pi with hardware attached on top. The Raspberry Pi is a controller and could be further designed to reduce hardware costs and energy consumption. Our system. Another task during the offline phase is pre-processing the floor plan. This includes specifying the installation locations of the beacons, confirming the delivery permitted areas, and marking special road surface such as tactile paving and contraction joints. Afterwards, we install the beacons at the designated locations within a station. The offline phase of the work is then completed. During the online phase, we also found some challenges in speed monitoring due to uncertainty of the sensor's placement and fluctuations in readings caused by special road surface. Therefore, before measuring speed, DIMO analyzes IMU readings to identify the sensor's placement, whether it's in the delivery worker's hands or on a trolley. Then, it detects and filters noisy readings from special road surface to ensure the accuracy of speed detection. As we began calculating the position, we encountered significant instability in the magnetic field signals within the subway stations. This made it a challenge to correct the positioning results by inferring the actual movement direction of the sensor. To address this, we utilized particle filter during localization to infer the target position. During this process, we converted the SSI2 distance model into a probability model for computation. Additionally, we integrated data from the accelerometer and gyroscope to determine the direction, and used historical trajectories to enhance the positioning accuracy. Our system can can detect 4 types of violations in real time and use a speaker on a sensor to remind delivery workers and nearby passengers. Any continuous movement at a speed exceeding 1.5 meters per second will be considered as speeding. Throughout the delivery process, deviations from the designated delivery routes will be continuously monitored. Fraud detection and geofencing are employed to determine unauthorized use of passenger lifts. Lastly, detailed delivery times are recorded to ensure compliance with scheduled delivery times. All violations are instantly alerted using a buzzer and logged in the background for daily reporting. Next, let me introduce our large language operation results and share the lesson we learned. During our system's operation, speeding violations were the most prevalent. However, there has been a significant decrease in the speeding violation rates, dropping from 19% in June 2020 to 2.7% by the end of 2022. Other violations also have a slight decrease, from 1% to 0.5%. This demonstrates a successful deployment of DIMO. By the way, we conducted A/B testing in 2 stations to exclude placebo effects. In conclusion, the accurate speed detection, indoor positioning, and real-time alarms are effective in changing delivery behavior. Compared to manual monitoring of delivery behavior, our system offers numerous advantages. First, effectiveness. DIMO can be deployed quickly with lower daily operational and maintenance costs. According to statistics, DIMO can save about 8 times the cost compared to manual supervision. Second, DIMO oversees a higher number of delivery instances. According to statistics, DIMO monitors 88% of delivery behaviors, whereas manual supervision only covers 53%. Moreover, after DIMO deployment, it can oversee all violations, leading to a significant decrease in violation rates. So, DIMO outperforms manual monitoring in detection violations. During large-scale deployments, we found that the beacons of different shapes have different failure rates. We noticed that car-shaped beacons had significant lower failure rates compared to cube-shaped ones. And the failure rates also vary in different areas. For instance, the beacons in the shop areas are most prone to damage, such as being bumped by passengers or delivery trolley. Therefore, we concluded that appropriate beacon deployment strategy can save maintenance costs in the long run. We also designed a questionnaire survey and interviewed 20 staff members from 12 subway stations to evaluate the operational status of our system. The questionnaire consists of 6 questions, including overall satisfaction, ease of use, effectiveness, detection accuracy, and so on. The results showed that DIMO received positive feedback from them. In addition to large-scale operation, we also designed a small-scale controlled experiment to test the accuracy of our system. The controlled experiment was conducted in 3 randomly selected subway stations with different area size and involved the collection of simulated delivery and ground truth data. The experimental results show that DIMO demonstrates higher accuracy in speed detection compared to directly measuring speed using localization results or integrating accelerometer readings. Our average error is around 0.3 meters per second, while the other two methods are 0.52 and 0.42 meters per second, respectively. Therefore, introducing road surface data detection can enhance the accuracy of speed detection. While testing the positioning accuracy, DEMO also demonstrates impressive performance. It can be observed that the integration of Bluetooth signals and IMU readings significantly improves the positioning accuracy of DEMO, compared to the average accuracy of 3.22 meters using a traditional logarithmic model. DEMO achieves an average error of 2.17 meters. Therefore, without labor-intensive fingerprinting, a customized eyesight distance model also can achieve accurate localization. In summary, we have proposed a practical real-time indoor delivery monitoring system. It has been successfully deployed on a large scale in Hong Kong, operating since 2020. Additionally, the system has a broad application scenario, such as malls and warehouse. We have also publicly released our experimental test datasets, along with some real delivery data. The data has been anonymized for privacy purposes, and we encourage everyone to download and use it. Thank you for your listening. Welcome any question.
Thank the speaker.